Good afternoon, everyone. My name's Gordon Brown. I am the Business Development Manager for Australia and New Zealand. I've been with ProSoft for about 3.5 years now, I think. And today we're going to be doing a webinar on antenna selection for radios. You don't need to take notes. We are recording the webinar for you, and we will send a link with the PDF of the slides, but feel free if you want to take additional notes. I'm going to try and answer all of the questions towards the end, if that's okay. There should be a little chat screen where you can send your questions in. Just before I start, there is another webinar scheduled for the 2nd of July. That is on 61850. We have one on the 9th of July on flow computing for oil and gas. And on the 16th of July, we have one on doing safety over wireless. So just for future reference. Right. I think it's about time to start. Antenna selection. So when we talk about an antenna, what the antenna does, it's going to direct the signal where it's most needed. A more focused antenna as opposed to a stronger antenna. When you think of antennas, what I'd like you to picture in your mind is the sprinkler attachment on the end of the garden hose. So if you've used them, you can either have water spraying quite wide, but it doesn't go very far, or you can adjust it more into a jet of water, and it'll go a lot further, but you obviously lose that width of the beam. And the same sort of thing happens with antennas. So we focus the radio's energy of where we want it to go. There's a few considerations we need to take when we're looking at antennas. One of them being what frequency. Are we using 900 megahertz? Are we using 2.4 or 5 gigahertz? Because these antennas, they're frequency specific. Also, how far are we communicating? Is this a few hundred meters, or are we going a kilometer or two, or is it 50 kilometers? This will determine what type of antenna we're going to use, as well as what type of radio. Some of the other points is, are we connecting just 2 points together, point A to point B, or are there multiple points that all need to be talking to each other at the same time? Some of these points might even be moving. Another consideration is the environment surrounding. Like buildings, is it indoors or outdoors? Is there metal in the area? Buildings? Are there trees? And also the distance from the radio to the antenna, more for mounting. The type of cable, and also the different connections. So on the screen here, we should see an antenna pattern. All antennas have different patterns. They'll send out a pattern that's horizontal as well as one that is vertical. So this one here is actually for a panel antenna. And the blue arrow can show us different circles. So one would be 0, -5, -10, -15, etc. What these are is this is signal loss. And the red arrow is showing us the angle where the beam is, where I would consider full strength. So obviously at the top there it's 0 degrees. It's definitely full strength. And as we move around to about the 30-degree mark, the antenna, that beam starts to lose some of the signal. So this, I would say, is a good 60-degree beam. It looks wider, but it's not that wide. So as shown with a little green triangle, that's the kind of antenna beam that's going to come out of it in horizontal form. The vertical will be different, obviously. So our most basic type of antenna is called an Omni. Generally quite a small little antenna. And what this does is it sends out a beam in 360 degrees, so all directions. This it will do horizontally, and then vertically on this type of antenna, it's going to be quite a wide vertical beam. It might be 70 or 80 degrees vertical. The next type of antenna, it's also an Omni, but it's called a collinear antenna. Basically what it is lots of little Omnis stuck together in a tube. And why we do this is with them sort of joined together, it increases the signal area. So it'll actually go out a lot further than normal. But where it's traveling further, that vertical beam is going to be a lot narrower, as shown in this next slide. If you look at the vertical beam in the antenna pattern on the left, with that red arrow, it's quite a wide vertical beam. And then on the right, when we're using the collinear Omni, it's a lot narrower. And then the more focused or stronger the antenna is, higher the gain, the narrower that vertical beam will be. So we need to consider this when we may have different elevations. You might have an Omni antenna on top of a hill, and it's sending out as far as possible in this narrow beam, and you've got something that's a lot lower on ground level trying to communicate to it. So just keep that in mind. The next antenna type, also very common, is a Yagi antenna. Now this would be similar to the type of antenna that we might find on our roof for the TV reception. It's a directional antenna, so it's not going to have that 360-degree beam. It's probably more like a 20 or 30-degree horizontal beam and 20 or 30-degree vertical beam as well. We generally use this if we want to get some sort of distance. This one over here, which we partly covered, is a panel antenna. The difference between this and the Yagi is this isn't going to go quite as far, but it's got quite a nice horizontal beam, so it gives you a wider coverage. Vertical beam would be very similar to the Yagi. The next antenna type is parabolic. It looks like a satellite dish. This is for long distance. I say long distance, we're looking at least 5 kilometers and up. Normally we would use it on 40 or 50 kilometer links. The beam coming out of it could be as low as a 6-degree beam, so it's more like pointing a laser at something rather than a nice beam. And then the last type of antenna that I wanted to cover is called a sector antenna. If you travel around, you may see them on some of the mobile towers. They're generally tall, thin, upright antennas, and they'll have a wide beam that could be anywhere from about 90 degrees to about 140 degrees. Vertical beam isn't going to be that great, and they're designed for a wide coverage. Those are your basic antenna types. The next type of antenna that we're going to move on to is what we call MIMO. It stands for multiple in, multiple out, MIMO. So this was introduced in 802.11n. And basically what MIMO does is it sends out multiple beams of information. These antennas that you see on the screen here, you'll actually notice there's multiple cables. That's because there's more than one antenna inside the antenna. And the radio even has 3 antenna connections. That is for MIMO. The types of places that we're actually going to use MIMO. So this would be in an enclosed area. Something like a warehouse. It might be a production facility. We've used them in mine shafts, food and beverage, automotive. If you can look at these 2 dots indicated with the arrows, the signal traveling from, I think it's point number 3 to point number 4, let's say that took 1 millisecond. You may have the same signal is bouncing off some objects, and that might arrive there in 1.2 milliseconds or 1.5 milliseconds. So it's getting the same signal at different times. So it's like an echo effect. So what the radio and the antenna does is it takes all these different signals as they arrive at different times and makes sense of it. So just a couple of examples. So top left here we have a brick plant. These are just generic pictures that I took off the internet. I want to show actual customer plants that we've done. So here you can see there's metal beams supporting up a metal roof. The walls look metal. There's metal machinery and all sorts of pipes and things. This is all stuff that would normally interfere with the radio. So you really need to use MIMO antenna in there. The bottom left picture, I think, is a dairy type process, and lots of stainless steel and metal. And that metal is going to reflect the radio signals, so it's going to bounce around quite a bit. Definitely need to use MIMO. Top right, you have some sort of steel mill, and bottom right, you have an aluminium smelter. All places where you'd be wanting to use MIMO. Some of these have cranes. We've done quite a few crane applications. Also considering the crane is metal as well. One of the more interesting applications that we've done with MIMO, one was actually down a mine shaft. So the mine shaft was about 1.2 kilometers. Here you can see we've put an antenna on the right there. We put it at the top of the shaft and one on top of the cage. So it's like a big elevator shaft. And this goes down over a kilometer. And there's a shaft next to it with a smaller cage. Because the shaft is that much smaller, we struggled a little bit with this, so we actually had to put multiple antennas on the way down. And we couldn't mount these in the shaft. We had to actually put them on the levels and angle the antenna against the shaft wall so it would bounce down the wall and reflect off the wall. Set up like this, we had about 98–99% accuracy. We were losing a couple of packets. And with this being a safety application over Wi-Fi, losing a couple of packets every now and again wasn't acceptable. So what we did was we used something called radiating cable or leaky feeder cable. It's the same thing. And what this is, referring back to my garden irrigation, it's like putting a soaker hose on the garden, one of those hoses with lots of little holes in it. And what it does is it basically lets the radio signal out of the cable. It doesn't travel very far. It's only going to go about a meter or two from the cable, but it'll travel all along the cable. So it's great for using in things like tunnels, and particularly in this application as well. So what we did, if you can look on the right, is a red line indicating the leaky feeder or radiating cable. We ran that down the side of the mine shaft, and we put additional antennas on the cage, on the little green square. And this was positioned probably about half a meter to a meter from the radiating cable. So we actually had redundant Wi-Fi links. And on the cage, what we did is we put one underneath the cage and one at the bottom of the shaft, also a separate Wi-Fi network. And what we do with it being safety and having redundant Wi-Fi links is we put them into what we call a PRP switch, so Parallel Redundant Protocol. And what the switch does is it receives two signals at the same time and drops one. So whichever one gets there first, doesn't matter, and it'll just ignore the other one. So you always have one of those links is going to be working. Just a few other applications where we've used radiating cable. So top left, this is a container shipping terminal. So if you can see, there's like a little fence there with some blue cable. What happens is the crane runs up and down there and it communicates to that cable. And previously, instead of having an operator sitting on top of the crane all day, only being able to operate one crane, he now sits in an office remotely. He's able to operate 3 or 4 cranes. So while they're busy unloading one of these cranes, he can then operate another crane, all over Wi-Fi. There's cameras so he can see what he's doing. In the middle, we've got a bottling machine. So with this bottling machine, it fills bottles, about 5 bottles a second. Previously, this was using slip ring technology. Now we've replaced the slip ring because you have wear and tear issues. And we do this with Wi-Fi using leaky feeder cable. The coke ovens run cable along the wall, and that charge car moves up and down. We've got a roller coaster ride. We've done multiple of these with the cable, and we've done ship loaders as well. Not this particular ship loader, but we've done a number of them in Australia, and also with safety over Wi-Fi. So some other considerations that you need is the connections. So pictured in the top left is a reverse polarity SMA connection, and that obviously pairs up with reverse polarity SMA male. If you choose to use your own cables and antennas, you do run the risk of using the wrong connector, damaging the radio, and damaging the cable. So you just need to make sure that you've got the correct connections, or that you use the ProSoft cables. Top right there is one of our cables. It comes with a nice right angle for installation. These are factory terminated. The other advantage with using the ProSoft cables is we know how they operate. We know the quality and standard, so we can just eliminate if we have any errors. We get different types of cable. So the cable on the left here, these two, it's what we call LMR 195. It's very thin and flexible. Generally, we would use this when we mount the radio inside a panel. We would use a short LMR 195 cable to the edge of the panel. And then there's a thicker cable, LMR 400. This we would use on the outside of the cable. So this thin cable has quite a high signal loss. That's why we want to use it as short as possible. And then the LMR 400 has got less signal loss through the cable. And then LMR 600, again, less than that. The 600 though is quite thick, difficult to work with. So we generally use the LMR 400. We like to try and keep the distance between the radio and the antenna as short as possible. Somewhere around sort of 2 or 3 meters. We definitely want to avoid going 30 meters. I'll give you an example of this. So here in the picture on the left, we've got a radio at the bottom next to the PLC, and instead of running 30 meters of antenna cable to my antenna on the roof, it's much better to use the example on the right. So we have the PLC at the bottom, and we use what we call a PoE injector, so power over Ethernet. And what this does, it'll carry an Ethernet signal to the radio, as well as power to the radio, and we can mount the radio close to the antenna. There's 2 advantages to this. Using long runs of antenna cable, you obviously have a lot of signal loss. So the Ethernet cable is going to give you a much stronger signal. And it's also a lot cheaper to run Ethernet cable than it is antenna cable, if you have any sort of distance to run. I just wanted to show a few examples of perhaps where things could have been done better. Again, some of these are just generic pictures. I've tried not to use customer pictures. The intention is not to embarrass anyone. It's more just so that we don't make the same mistake. So on the top left here, we've got a parabolic antenna. What the customer had previously done was they had 2 Omni antennas, and for some reason they weren't getting a very good signal. So they thought they would use a stronger antenna, or more focused antenna is what they actually got. Parabolic, it's like trying to line up a laser pointer with something that's moving, so the signal was even worse. What would have been much better here, I think it was a crane application, would be to use 2 panel antennas, one on the crane and then one obviously where this parabolic antenna was. The next picture along shows us an Omni antenna, and there's a red circle showing an Omni in the distance. Again here, Omnis sort of 15, 20 years ago, they were very popular. But one of the downsides of an Omni antenna is it sends out a signal in 360 degrees. So a lot of the energy and power of this application is wasted. The signal only needs to go in one direction, but it's As well as sending the signal, it's also receiving a signal. So if you can picture yourself in a room and we're having a conversation, and there's about 4 people around you, and they're also talking to you as well while you're trying to listen to me, it's very hard. And it's the same sort of thing with the radio. The Omni antenna is going to pick up all of the radio signals around it, not what you want it to pick up, but everything else. So interference for the radio. Much better to use a directional antenna if it's just point to point. Top right and bottom right, we've got excess cable. The more cable, the more signal loss. The other thing with the picture on the bottom right is it's quite thin cable. It's probably some type of LMR 195. It'd be much better to use a thicker cable. And obviously not as long. That doesn't need to be coiled up. Some other common mistakes. Here we've got the Omni again, communicating to an Omni in the distance. Now, generally antennas like clear line of sight, so they like to be able to see each other without objects in between. So that cable tray or bridge, whatever it is in the middle, that's an obstruction. It's going to interfere with the signal. Also, it's going to be a weak signal because that signal, both of them, are spread in all directions and it's picking up interference. So if I had to do this radio link, I would want to use MIMO here because of the metal and try and bounce it off the buildings. Try and get a clearer line of sight and use a directional one like a panel antenna. Get a much stronger signal and less interference. Next picture with the big yellow steel structure in the background. So we've got an Omni mounted against a big yellow steel structure. Now what happens with the Omni is it sends out the signal in all directions. So the first thing, the signal hits this metal, bounces back and then starts interfering with itself. This is a standard Omni antenna. It'd be much better to use MIMO and to actually move the antenna away maybe half a meter or a meter from that yellow structure. The next picture, stainless steel cupboard. This customer wasn't sure why his radio reception was so bad. He had mounted the radio and the antenna inside, where traditionally you would mount the antenna on the outside because it's not going to travel through that metal very well. Top right, we have an AGV. This is in a warehouse. It's probably one of the cheapest type of antennas you can get. Looks like a $10 or $15 antenna, where they should be using a MIMO antenna. And bottom right, we've got 2 antennas very close to each other. These, although they're directional antennas, they will have side lobes, so there will be a bit of signal coming out the side, and these 2 will be interfering with each other. It'd be much better if you could separate those 2 antennas and get about a meter or 2 distance between them. The other thing, before we do any kind of radio installation, is to check what radio signals are there in the first place. So we want to make sure our radio signal is clear, and we also want to make sure we don't interfere with existing radio equipment. So this particular instance, they called us up, we went through and did a quick scan, and it turned out the IT department was installing radios interfering with the production. So we changed the antenna type, we changed the frequency and the band, and then everyone was happy. But this picture shows very congested 2.4 gigahertz. We do offer a Wi-Fi service where we can come and scan and check the area for you. And we can even bring through equipment and test as well. That's pretty well what I wanted to cover on the antenna selection. So I'm going to open it up to questions if anyone has any questions out there. There is there should be a little Q&A box if anyone's got any questions on an antenna selection. So this will be recorded, so we'll send you the links afterwards where you can download, and we'll also send you the notes. And if you keep an eye out on LinkedIn and your email, you'll see some of the other webinars that we're going to be covering in the next few weeks. Just wait a minute or two to see if there's any questions coming through. Yes, I have a question here. Can we tie in two directional, say 180-degree antenna to a single radio instead of using Omni? Yes, we could. Depending on how wide a beam you wanted, I probably wouldn't use two 180 degrees. The reason being, when we use something like that, what we're going to do is probably use a splitter. So it's going to split the signal. When you split the signal, you halve the power. So it's probably better just using Omni if you need that. If you needed to send, let's say, a signal east and a signal west, so directly opposite, you could, and you could probably use something like a Yagi. That I would recommend, where we put in a splitter, put in your Yagi facing either way, and just have them not too close to each other. What about antennas used to transmit over sea? What is the best choice? So my personal one is my personal favorite is a panel antenna. It's going to depend on the distance. So we've done transmissions about 40 or 50 kilometers out to oil rigs at sea. This was particularly difficult. We used a parabolic antenna, which to cover that sort of distance, you're going to need parabolic. But obviously the land was stationary and the oil rig moves up and down slightly. So it was a little tricky to line up. You need specialized equipment. So I would say it all depends on the distance you want to travel. The further you want to travel, the more focused the antenna needs to be. Any other questions? Right, I think that's all the questions, so I'll probably call an end to it, and we'll send out the video and links. If you have any others afterwards that you might think of, feel free to contact your regional sales manager. He can probably put you in contact with myself or one of our other technical people. Thank you very much for attending today, and thanks very much.